The replication stream protocol defines the mechanism by which data mutations propagate from a primary node to replica nodes within a distributed system. The protocol operates on a principle of sequential consistency, wherein each mutation is assigned a monotonically increasing logical timestamp. These timestamps ensure that all replicas apply mutations in identical order. The protocol does not guarantee causal consistency across independent write streams. Mutation ordering is enforced through a central sequencer component. The primary node maintains a write-ahead log known as the mutation buffer. Each mutation is written to durable storage before acknowledgement to the client. The buffer is organized as a circular queue with fixed size. When the buffer reaches capacity, the oldest entries are eligible for truncation. Truncation occurs asynchronously and does not block write operations. Replicas maintain a corresponding read offset that tracks which mutations have been consumed from the primary's log. Replication operates in two modes, synchronous and asynchronous. Synchronous replication requires that at least one replica acknowledge receipt of each mutation before the primary considers the write durable. The confirmation latency is measured from mutation arrival at the replica to durability acknowledgement. Asynchronous replication does not require replica acknowledgement. The primary immediately returns success to the client. Asynchronous mode introduces a bounded window of potential data loss in the event of primary failure. The replica to primary heartbeat mechanism operates at configurable intervals. Default interval is 500 milliseconds. Replicas transmit their current read offset to the primary at each heartbeat cycle. The primary uses this information to determine which mutations have been fully replicated. A mutation is considered safe when all non-failed replicas have consumed it. The safety status affects whether the mutation can be garbage collected from the mutation buffer. Replica lag is defined as the difference between the primary's maximum assigned timestamp and a replica's maximum applied timestamp. The protocol monitors lag continuously. When a replica's lag exceeds a configurable threshold, the primary initiates backpressure on incoming writes. Backpressure pauses new mutations until the replica catches up. The default lag threshold is 10,000 mutations. Backpressure ensures replicas do not fall arbitrarily far behind the primary state. The mutation format consists of a fixed header followed by a variable length payload. The header is 32 bytes and contains the assigned logical timestamp, the source transaction identifier, and a cyclic redundancy check code. The payload contains the serialized mutation data. Serialization uses a schema-aware binary format. The maximum payload size is configurable with a default of 1 MB. Mutations exceeding the size limit are rejected at write time. When a replica connects to the primary after a disconnection, the primary performs a state reconciliation operation. The replica provides its current read offset. The primary identifies the range of mutations the replica must apply. This range is established through a binary search on the mutation buffer. If the required mutations are no longer in the buffer, the primary initiates a full snapshot transfer. Snapshots are created on demand and contain the complete state at a specific timestamp. Snapshot creation uses copy-on-write semantics to avoid blocking the primary's normal write path. The snapshot process reads the current state at a fixed timestamp, creating a logical view. Snapshot data is serialized incrementally and streamed to the requesting replica. The snapshot is self-describing and includes metadata for validation. The replica applies the snapshot as a single atomic operation, replacing its current state. No mutations are applied during snapshot installation. Conflict resolution occurs when a replica applies mutations to state that may have been modified locally. The protocol does not permit local writes on replicas in primary mode. In certain deployment scenarios, dual write configurations exist where replicas also accept mutations. In such cases, conflicts are resolved using a timestamp-based ordering rule. The mutation with the lower timestamp is discarded. Simultaneous mutations at identical timestamps are resolved using replica identifiers as a tiebreaker. The mutation buffer employs a time-based retention policy alongside capacity-based retention. Mutations are retained for a minimum duration configured as the retention window. Default retention window is 24 hours. After the retention window expires, mutations become eligible for truncation when buffer capacity is needed. Mutations required by active replicas are never truncated regardless of retention policy. The retention mechanism ensures a recovery window for temporarily disconnected replicas. Error handling for mutation application failures distinguishes between transient and permanent errors. A transient error such as a temporary resource constraint does not advance the replica's read offset. The replica retries the mutation in the next synchronization cycle. A permanent error such as a schema violation is logged, and the replica advances the offset without applying the mutation. The primary is notified of permanent errors. A replica with excessive permanent errors is flagged for investigation. The replication stream uses TCP connections with configurable timeouts. Connection keep-alive is maintained through periodic ping messages if no mutations are transmitted. The keep-alive interval is half the configured heartbeat interval. When a connection is lost, the replica immediately attempts reconnection using exponential backoff. Initial backoff is 100 milliseconds. Maximum backoff is 30 seconds. The backoff is reset when a connection succeeds or the primary is changed. Metadata associated with each mutation includes the source client identifier, the transaction identifier, and mutation type information. The source identifier allows the primary to correlate mutations with client requests. Transaction identifiers enable grouping of related mutations for atomicity. Mutation type information indicates whether the mutation is data modifying or a control message. Control messages include snapshot markers and replication state changes. Control messages are processed separately from data mutations. Monitoring and observability of the replication stream expose metrics including replica lag, mutation throughput, and buffer utilization. Lag is measured in both mutation count and wall clock time. Throughput is reported as mutations per second. Buffer utilization is reported as a percentage of maximum capacity. These metrics are sampled at 1-minute intervals. Time series data is retained for 7 days at the default resolution. Alerting can be configured on any metric threshold. Configuration of the replication stream is stored in a configuration document using a human-readable format. Parameters include buffer size in megabytes, retention window in hours, and heartbeat interval in milliseconds. All parameters are immutable until explicitly reloaded. Configuration changes are applied atomically. If configuration is invalid, the system logs an error and uses previously valid configuration. Configuration validation occurs at startup and during runtime reload operations. The replication stream protocol provides eventual consistency semantics under normal operation. All replicas will eventually contain the same mutations in identical order. During network partitions, the primary continues accepting writes while isolated replicas serve potentially stale data. After partition healing, the secondary replicas resynchronize with the primary. Mutations applied on isolated replicas that conflict with primary mutations are discarded. The replication stream documentation is maintained in the specification.